Love the calculators, but to get full credit on assessments in our class, you have to justify your answers with some algebra. You got to be able to show us some algebra and some analysis to reason why something is true. So here we have some problems where we're first going to figure out what the limits are as we approach a point in an example where you can literally just plug in the number. So this is a simple little quadratic. I'm going to stick in the number 3 and see that I end up getting 3 squared minus 3 plus 1. 9 minus 3 is 6. 6 plus 1 is 7. And since a parabola is a pretty chill function, nothing crazy going on, this is clearly just going to be the answer because it's the behavior that's occurring close to 3. It'd be nice if we could just always just plug in numbers, but sometimes that's not the case. So look at this particular example where we have a function and it's piecewise and x is approaching 3. So if we were to just plug in 3, we would be following the top branch where it says x is less than or equal to 3. And so f of 3 would be equal to 2 times 3 is 6. 6 plus 1 is 7. However, if we were to do a limit as x approaches 3 from the left, that means we'd be following the top branch, which we already did. 2 times 3 plus 1 is 7. But if we were doing a limit as x approaches 3 from the right, then you'd be coming in along the bottom branch because 3 plus would mean a little bit bigger than 3, and 3 squared is 9. So since these are not equal, it turns out that the actual limit as x approaches 3 overall is actually a does not exist. Limit does not exist. So limits don't always exist, even when functional values do. And that is just something that we have to deal with in different types of functions. It happens often during the piecewise ones, but sometimes they'll match up on us. But in this example, we have a limit not existing, even though the functional value does. So it's not as easy as just plugging in. Example 5 actually asked us to find the one-sided limits. I already did that above. When I was doing a left-hand limit, I come in on the top branch. Right-hand limit, come in on the bottom branch. So let's try this example here. It says find values of k that will make the limit as x approaches negative 2 exist. So we need the left-hand limits and right-hand limits to be equal. So what is the limit as x approaches negative 2 from the left of the f of x? That means we would be following the top rule, and the top rule would be giving us negative k squared multiplied by negative 2 over 2 minus 12. Cancel the negatives, cancel the 2's, and it looks like we're getting k squared minus 12. So the limit from the left is k squared minus 12. How about from the right? If we come in from the right, we can see that we would be coming in along the bottom branch, which would be giving us a k times a negative 2 squared, which of course would be a 4k. So now the limit from the left is k squared minus 12, the limit from the right is 4k, and if we want this limit to exist, we need these to be equal to each other. So I'm going to set them equal to each other. This would force k squared minus 4k minus 12 to be equal to 0, k minus 6, k plus 2 equals 0, and so k would either be 6 or negative 2. So if k were 6, then the limit as x approaches negative 2 of this function would be, remember the limit was 4k, so if it were 6 it would be 24, and if k happened to be equal to negative 2, then the limit as x approaches negative 2 for f of x would be 4 times negative 2, which is negative 8. And that concludes the finding the value of the limit in the two cases. So we can do some algebra in here, right? We could make things much harder or much more complex in the future by using logarithms or exponentials. So we have to remember everything that we've ever learned. How does the behavior near vertical asymptotes happen? Well, remember back in the unit on rational functions that vertical asymptotes occur when you're dividing something that's not 0 by 0. So the standard way, vertical asymptotes will always be either positive or negative infinity on regard or depending on which side they're coming in from and various pieces or in various things that are true about the function itself. So when we're trying to see if this is going to be a vertical asymptote problem, first thing I'm going to do is I'm going to plug in 3, because remember, if we can just plug it in and get an answer, that might actually be the correct answer. But as we can see here, if I plug in 3, I'm going to get 1 over 0, means this is a vertical asymptote. Answer is probably plus or minus infinity. 1 of plus or minus infinity. So let's make a number line. On that number line, I'll put the number 3, and then I'll test the intervals to determine if it's positive or negative, if this rational function is positive or negative. And on the right-hand side, we know it's positive. Plug in a number bigger than 3. And on this side, it would be negative. And so as I approach 3 from the left, I'm on the negative portion, so my answer is negative infinity. For this example, again, you stick in negative 2. Numerator is negative 6. Denominator is 0. This is a vertical asymptote case. This is either plus or minus infinity. Make a number line. The two critical points are 4 and negative 2. And if I test the intervals here, I can see that the positive, positive, positive is going to go over here. And then as I go less than 4, this will be negative and this one will be negative. And so as I approach negative 2 from the right-hand side, I can see that I'm in a negative portion. And therefore the answer is negative infinity. How about the limit as x approaches 0 of 1 over x? So again, plug in 0. This is 1 over 0. This is a vertical asymptote case. It's probably plus or minus infinity. One of these two. Let's plug in 0 is my critical number. Positive on this side, negative on this side. And uh-oh, the 0 didn't say left or right. And I can see here that on these two sides, I'm getting different values, a positive infinity and a negative infinity, so this limit actually does not exist. How about if we were going to approach 1 from the left on this function, 2 different x-intercepts, 2 different vertical asymptotes. Stick in 1, 1 plus 1 is 2, times negative 4 is negative 8, over 0, so we're again a vertical asymptote, or plus or minus infinity. Make a number line so we can see what it becomes. We're going to get a negative 1, and a 1, into 3, into 5. If I were to test out all the intervals, I can find out just by plugging in numbers. I get plus, minus, plus, minus, plus. And so as x approaches 1 from the left, the answer is going to be negative infinity. Let's do 2 more of these. If I were going to approach 1 from the right-hand side, I actually already made a number line for this, so I'm just going to look back up here and look what happens when I come in from the right-hand side of 1. And there now I'm on the positive interval, so that answer would be plus infinity. Finally, on this example, if I stick in the number 2, 4 minus 6 is negative 2, minus 10 is negative 12, over 0. Vertical asymptote, probably plus or minus infinity. The top factors, x minus 5, x plus 2, which is going to help me to make my number line where I'm going to get a negative 2 into 2 into 5. And this time if I start to test numbers, I'm going to get a positive over here, and then multiplicity 1 I'm going to switch, and then 2 is in the bottom. It's a double multiplicity because of absolute value, and then on the far end we get a plus. So as I approach 2 from the left-hand side, I can see that I'm getting in a negative interval. The answer is negative infinity. So in general, vertical asymptotes are either plus or minus infinity. This is sufficient analysis to let me know that you understand all of the pieces that are going in and you didn't just A, plug in a number, or B, use a graph. You're actually showing me the analysis, showing me the algebra. Now 0 over 0 is really curious. 0 over 0 is called the indeterminate form because it could be equal to absolutely anything, or it could be equal to nothing, or it could be infinity, or it could be does not exist. It could be a whole bunch of different examples, and essentially they're all of those answers at the same time. So in example 10, for doing a limit as x approaches 3 negative 3 of x cubed plus 27 over x plus 3, it turns out that negative 3, if we were to plug it in, would be negative 27 plus 27, 0. Negative 3 plus 3 is 0. Indeterminate means you need to do something. And what we're going to do is we're going to change the problem by performing some algebra. X plus 3, x squared minus 3x plus 9 from the sum of cubes formula over x plus 3, which allows me to cancel out the x plus 3's and leaves me with the limit as x approaches negative 3 of x squared minus 3x plus 9. Now, like we talked about in our very first example, I can just stick in negative 3 to see what I get. Negative 3 squared is 9. Subtracted by 3 times negative 3 would be plus 9, plus another 9. This answer is 27. Next degree, let's turn it up a notch. X goes towards negative 3. In the numerator, we have 9 minus 18 plus 9. 9 minus 3 is 6, minus 6 is 0 in the denominator. 0 over 0, time to do something. What will we do? Let's try some factoring. Top is x plus 3, quantity squared, and the bottom becomes x plus 3 times x minus 2. One of the copies of x plus 3 cancels, and that means now the problem that was giving us 0 in the bottom has been eliminated. Negative 3 plus 3 over negative 3 minus 2. The answer in this case is 0. Next, as x approaches 1, how do we figure out what the let's factor this polynomial, this cubic polynomial. How do we find the zeros and start factoring a cubic polynomial? This is going to be p's over q's, right? Well, let's first check if we actually need to. Let's go stick in 1, because if it just works, maybe that's the answer. 1 plus 1 is 2. 2 minus 5 is negative 3, plus 3 is 0. 1 minus 3 is negative 2, plus 2 is 0. There's our indeterminate form. Now we're in the factoring stage, so I have to factor the numerator. Limit as x approaches 1. Since the numerator is 0 when x equals 1, as verified over here, I don't need to do all the fancy rational roots tests. I can just say that 1 goes in and do the synthetic division. I already knew 1 goes in because I tested it when I was finding out it was an indeterminate form. So carry down 1, 1, that comes a 2, 1, negative 3, 0, and so the numerator is going to be x minus 1 times x squared plus 2x minus 3, which if I were to continue that factoring would actually be x minus 1, x plus 3, and x minus 1. How about in the denominator? X cubed minus 3x plus 2. Again, I know 1 is already a 0, so I'll synthetically divide that. 1, 0, negative 3, 2. Carry down the 1, 1, 1, 1, negative 2, negative 2, 0. Sweet. On the bottom, I'm getting x minus 1. X squared plus x minus 2. So I get x minus 1. X plus 2, x minus 1. Great cancellations. And now that all of the zeros that were in the bottom are gone, I can plug in the number 1. 1 plus 3 is 4. 1 plus 2 is 3. Finally, let's take a limit as x approaches 9 on this problem. Stick a 9 on top, it would be 0. Stick a 9 on the bottom, 3 minus rad 9, 3 minus 3 is 0. It's indeterminate. So this time, let's try rationalizing the denominator. Multiply by 3 plus rad x on top and bottom. In the numerator, we will end up having 9 minus x multiplied by 3 plus rad x. In the bottom, this is a difference of squares being multiplied, so we get 3 times 3, which is 9, rad x times rad x, which is x. And look at that beautiful cancellation, meaning now we can plug in the number 9, 3 plus rad 9 is 3, so 3 plus 3 is 6. So when you're dealing with the indeterminate form, you got to pull out all your algebra from all the algebra we've ever learned and then use appropriate techniques to simplify. And then plug in. 2 more examples. Let's do this complicated limit. So, as I plug in 0, 0 plus 9 is 9, rad 9 is 3, 3 minus 3 is 0, bottom is 0. It's indeterminate again. Let's multiply top and bottom by the conjugate. Rad x squared plus 9 multiplied, rad x squared plus 9 plus 3, rad x squared plus 9 plus 3 would yield limit as x approaches 0 of numerator becomes x squared plus 9 minus 9 over x times radical x squared plus 9 plus 3. 9 and 9 cancel. Once those are canceled, one of the copies of x will cancel, leaving me with limit as x approaches 0 of x over radical x squared plus 9 plus 3. Sticking in 0, now that we have no longer a 0 in the bottom or an x in the bottom that was such a pain, we get 0 over rad 9 is 3, 3 plus 3 is 6, and so the final answer here would be 0. And as one last example, let's do the limit. Here, this example, we're going to find all 3 of these limits. All 3 of these limits. X approaches 0, x approaches 1, x approaches 2. In this piecewise scenario, 0 is a critical number, right? Something important is happening at 0. Let's see if the limits match up. The limit as x approaches 0 from the left of g of x. From the left means we'd be following the top branch. 0 minus 1 is negative 1. Limit as x approaches 0 from the right means we'd be following the middle branch. 0 squared is 0, 0 plus 1 is 1. Uh-oh, the limit from the left and the limit from the right don't agree, so limit as x approaches 0 would be does not exist. Second problem, how about the limit as x approaches 1 of g of x? 1 is completely inside of the interval 0 to 2. So if I'm approaching 1 from the left or the right, as long as I'm close to 1, I'm just going to be on this parabola. So there's no issues here, no piecewise issues we have to worry about at all. So 1 squared is 1, 1 plus 1 is 2. There's your final answer. This limit would be 2. Finally, as we approach 2, again we have this place where we're moving between branches, so we're going to have to do these separately. Limit as x approaches 2 from the left of g of x would mean we'd be plugging 2 into the middle branch. 2 squared is 4, 4 plus 1 is 5. Then g of x from the right of 2 would give me the bottom branch. Negative 2 times 2 is negative 4. Negative 4 plus 5 plus 9 is 5. This time the two sides agree, and therefore the limit overall would be 5.